Good evening, members. You're most welcome to our seminar today. It's our last seminar this year, and our speaker is Dr. Annet Kyomuhangi. She's our own. We know her. Most of us know her, definitely. So she's going to talk about local and nilradical for modules over commutative rings. Dr. Annet, you're most welcome.
Thank you so much, Sarah, for that welcome. Good evening, everyone. As Sarah has told you, I'm Annet Kyomuhangi from Bositema University, and I'm going to talk about the local nilradical for modules over the commutative rings. I'll start with the preliminaries, then I talk about the locally reduced modules, which I call the A-reduced modules. I give properties of the local nilradical, A gamma. I also gave its applications. Then I'll compare it with other radicals that are already known. Yeah, and lastly, I'll give the references. So when I talk of a ring, then I mean a commutative unitary ring. R mod will denote the category of R modules, and the submodule will be denoted by this. If I talk of gamma AM, then I mean the A torsion submodule of M, and left multiplying it by A, which is an element from the ring, will give me what I call the local nilradical of M. So home, as you all know, it's just a group of R module homomorphisms from one module to the other. So we say that a ring is reduced if for all elements of the ring, A, if we have A squared equal to 0, then it implies that A is equal to 0. Ali and Zhu generalized these reduced rings to what we call the reduced modules. And we say that another module M is reduced if for all elements A of the ring and elements M in the module, A squared M equal to 0 implies that AM is equal to 0. So this is just equivalent to saying that for positive integers K, AKM equal to 0 implies that AM is equal to 0. So you can use these two interchangeably. A squared M equal to 0 implies AM equal to 0, or AKM equal to 0 implies that AM is equal to 0. So previous studies, as you can see from the definitions that I've given, they are all element-wise. We are looking at elements of the ring and then elements of the module. So this study looks at reduced modules in terms of factors. We are looking we are describing them in terms of homomorphisms and then the objects. And we say that a factor from a category of R modules is idempotent if this property is satisfied. In case it is a pre-radical, then we must have, for any homomorphism, we must have this property satisfied. And if we have a pre-radical which satisfies this other property, then we say that that pre-radical is a radical. Also, if a functor is left exact, then that functor must be preserving left exactness. In other words, if you have a left exact sequence, applying such a functor onto it keeps it left exact. Equivalently, one can define a left exact functor using the submodule of a module. If you have such a submodule n, applying this functor onto n is equal to applying this functor onto m intersection m. So one can use either of the two. You can use the sequence or you can use this property. So if you find that such a functor satisfies this property, then we say that that functor is left exact. We all know that an element, if you have an element of the module, say M, it is I torsion if it is being annihilated by powers of this ideal I. And taking the collection of these I torsion elements of the module, then we define what we call gamma IM, which can also be defined this way, the union of all these elements of the module that are annihilated by powers of I. So we find that this gamma IM is a submodule of M. Sorry, it is a submodule of M, and it can also be described categorically. It can be, it is equivalent to the limb home. And we say that another module M is I torsion if applying the I torsion, gamma IM is equal to M, and it is I torsion free if gamma IM is equal to 0. So having seen that gamma IM is equivalent to the limb home, then we see that it can be described in a categorical form, that is by modules and then the homomorphisms. So one is able to define a functor of this gamma I from a category of error modules to a category of error modules this way. So you have gamma I applied to M to have the gamma IM. And we find we find that that if you take I to be a principal ideal, if it is generated by a single element of the ring, then we find, say A, we find that gamma AM is actually equal to gamma IM. For instance, if we take a ring to be a ring of integers, and we look at the ideal, which is generated by prime numbers, then we find that the Z module ZPK is, so Z, we are taking the error module, which is now the Z module ZPK. We find that gamma with respect to this ideal is actually the same as gamma with respect to the element P. And this also acts as an example for the I torsion modules. So we find that applying gamma onto this module ZPK actually fixes it. So we have a P torsion module, which is ZPK. More properties of this I torsion is that it is idempotent and it is left exact based on the properties that I shared, the definitions I shared for the functor. So we find that gamma I is idempotent and it is also left exact. In other words, it preserves left exact sequences. However, it is in general not a radical, but over a Noetherian ring, then we find that this gamma I is a radical, and it also preserves injective modules. And because it preserves injective modules, then one is able to move to the right derived functor of it, which we call the local cohomology. So the ith local cohomology is naturally equivalent to the limb of XTI. We all know that the derived functor of home is the XTI. So because we have gamma I, which is equivalent to limb home, then its derived functor will be the limb of XTI. And this takes us now to looking at the relationship between this gamma, the I torsion functor, and then the reduced modules. So we have seen the definition of the reduced modules. Here we now introduce the local definition of reduced, where we have to define the reduced modules in terms of a single element. So we are saying that another module M is A reduced if for all M in M. A squared M equal to 0 implies that AM is equal to 0. So a module will be reduced if it is A reduced for all elements A of the ring. So that is why we say that this is A reduced is locally reduced, because we are describing it with just a single element of the ring. We shall say that a ring is A reduced if it is A reduced as an error module. Some of the examples of reduced and A-reduced modules include free modules. You're looking at free modules defined over a reduced ring, are reduced. And because reduced modules are closed under submodules, direct sums and products, we find that projective modules also defined over reduced rings are also reduced. Why? Because projective modules are direct sums of free modules. So we also have the vector space also reduced. And we find that the A torsion free modules are also reduced, A-reduced. We carry on and now look at how we can relate the modules being A-reduced and relating them to the A torsion module, the A torsion submodule. So we find that if you have an ideal, which is a principal ideal just generated by an element A in R, then we have the following equivalent. We find that M, another module M, is A reduced if and only if A gamma AM is equal to 0, and the annihilators of I mean the collection, the elements that are annihilated, elements of the module that are annihilated by A being equal to elements of the modules that are annihilated by powers of K. And then the limb home is isomorphic to home. And finally, because this property is true, then this brings us to the gamma AM being isomorphic to home of R factor A, because we mentioned before that gamma AM is equivalent to the limb home. So this gives us an equivalence. And because we now have gamma AM equivalent to home, that means with our reduced, the A reduced modules, they help us to simplify these computations. Why? We find that now the limb home that we had, the limits have been dropped. So this proposition as well can be applied in general for modules that are reduced. So it is a matter of having for all elements A in R, then we have the similar proposition. And we can also use this very proposition to characterize the reduced rings, where we take M to be R, and we find ourselves with A gamma AR being equal to 0. So one can also be able to describe or to characterize the reduced rings using this the ring and then the homomorphisms. So this pushes us to knowing that, oh, now this A reduced and then the reduced is actually a categorical property. Why? Because one is able now to describe these modules that are A reduced or reduced using the objects and their homomorphisms. So having known that this property is categorical, then one begins thinking of how to define a functor that actually describes these reduced and irreduced modules. So we define a functor by just left multiplication of A on 2 gamma A, which is the A torsion, and by left multiplication, we find ourselves taking all elements of the module M, left multiplying them by A, which is a fixed element. So you have AM such that M is annihilated by powers of A. And we find that actually this functor is a radical. Remember, initially, we said that gamma A, the A torsion functor, is not a radical in general. It becomes a radical when we are describing it over a Noetherian ring. Surprisingly, when you left multiply this I torsion functor by an element of the ring, then we find that you obtain a radical without any condition of Noetherianness. So this A gamma A is what we call the locally nilradical. And describing it with in terms of reduced modules, we find that another module M is A reduced if A gamma AM is equal to 0. So we go back to our definition here. We are saying that another module M is A reduced if A gamma AM is equal to 0. When it is equal to 0, that means you have AM equal to 0. such that AKM is equal to 0. Remember, our A is just a single element of the ring, and this takes us back to the definition of A reduced. So with the A gamma AM equal to 0, we find that the module is A reduced. And so it will be reduced if A gamma AM is equal to 0 for all elements A of the ring. We also note that whereas gamma A, the iteration functor, which was idempotent and left exact, we find that with this locally nilradical, after left multiplying the iteration functor, we find that the functor ceases being idempotent, no left exact. Because based on the property of the idempotence, when you again apply A gamma A onto A gamma A, then you'll find yourself with A squared gamma A, which ceases being idempotent. So I give an example of showing that it is not left exact. If we take a ring to be Z and another module, which is now the Z module, Z8, and its submodule to be Z2Z8, then if we consider an element of Z2, we find that applying our property for left exactness, we find that 2 gamma 2 into 2Z8 is actually equal to 4Z8, which is contained in 2Z8 that is equal to N intersection 2 gamma 2 to Z8. And yet we expect to find, we should have found that this 2 gamma 2N, because we are applying the functor A gamma A, applying it on 2N, we should have expected it to be equal to N intersection 2 gamma 2M. But because we find that it is actually contained in 2Z8, so we conclude that this functor is not left exact. However, this functor, when you consider a subcategory of reduced modules, then we find that this functor is left exact. So we define a submodule of another module M to be characteristic. If you get all automorphisms F of M, applying on that submodule, we find that it is contained in N. So we have some other properties of this locally nilradical. We find that if we take your M to be R, then we find that A gamma AR is an ideal of R. It is actually a nil ideal of the ring. And we also find that A gamma AM is a characteristic submodule of M, and this property is satisfied. But if we happen to find M projective, then we get an equality of this property. When we take NR to be the nilradical of the ring, that is, you're collecting all nilpotent elements of the ring, and we look at the module analog of this nilradical, which is the envelope of the 0 submodule, defined by AM such that AKM is equal to 0, then we find that this envelope is actually the union of A gamma AM. Why? We have said that A gamma AM is you're collecting all AM such that AKM is equal to 0, but for a particular element of the ring. Whereas for this case, we are looking at elements, all elements A of the ring. So this gives us the union of A gamma AM, and hence a stratification. We find that this becomes a stratification of the envelope of the zero submodule. And taking, if you happen to take M to be R, then we find that we obtain the nilradical. The nilradical, which is equal to the union of A gamma AR. And actually, this is where our title comes from, because we find that this nilradical now can be studied locally. How? Just look at this A gamma AR, study it, get its properties, and then take the union of all these. You will come up with the nilradical. So this, you're looking at it for each element of the ring, and so you're basically looking at the nilradical locally. So that is why we defined this funct of ours to be the locally nilradical. So this functor A gamma A generalizes both the nilradical and then the A torsion functor. We look at more properties of this local nilradical. We find Lam showed that this property is satisfied for the polynomials on this nilradical. We also find that our radical A gamma A, which is the local nilradical, satisfies the same property. And this deduces to a ring being A reduced. If you have a ring A reduced, then we find that actually the polynomial ring corresponding to that R is also A reduced. Why? Because if you have a ring A reduced, then this A gamma AR will be equal to 0, meaning that you have A gamma A into this polynomial ring equal to 0. So making the polynomial ring A reduced. And in case you have vice versa, in case you have this A gamma AR equal to 0, then that tells you that this is equal to 0, and hence gamma AR is 0, meaning that your ring R is A reduced. Yes, we continue with the properties of this radical, and we define the Frobenius functor. So you define it over a Noetherian ring of characteristic P, which is greater than 0. And the interesting bit of this Frobenius functor is that it is exact when the ring is regular. We also know that when the ring is regular, then every R module is reduced. And what does this imply? If you have a module which is reduced, then that means your A gamma A M is equal to 0. And so we are able to define a functor A gamma A to be the 0 functor. So having a Noetherian local ring of characteristic P, we find that the Frobenius functor is exact on the category R mod. A gamma A, which is the local nilradical, is a 0 functor on the same category with every module reduced. Yes, and more to the applications of these reduced modules. If we take the ideal to be generated by just an element, A, then we find that M, if our module is A reduced, then the ith local cohomology reduces to XTI. Remember the definition of the ith local cohomology was, it was equivalent to the limb of XTI. But because our module is A reduced, the A torsion functor reduces from the limb home to home. So the limit is dropped. And so the derived functor of home is just the XTI. So we find that instead of now computing this direct, a chain of modules to get the local cohomology, one is able to compute it fast. It is easy to compute because the limits are now dropped. You're basically looking at just a single module. In case R factor I is a projective error module, then we find that this local cohomology vanishes. Okay, we go to a collection of, we are looking at a collection of torsion elements. We know that a collection of torsion elements is actually not a submodule of M. But if our ring is reduced, then we shall find that this set actually becomes a submodule of M. And so having it as a submodule of M over this reduced ring, then we can also stratify this torsion submodule and have it as a union of gamma AM when our module is reduced. Remember the definition of gamma AM, you're collecting all M for which these elements are annihilated by powers of A. But now, once our module is reduced, then now we drop the power on A and have it defined this way, but for a fixed element of A. And because this is a collection of all these elements that are annihilated by A, we are looking at all these elements, non-zero elements of the ring, then we find that it is actually taking the union of all these gamma A's for all these, the union of all gamma A's with respect to the non-zero elements of this ring to give you the torsion submodule. We compare this locally nilradical with other known radicals, the already existing radicals. We have the A sim prime radical, which is just the intersection of A sim prime submodules of M. The sim prime radical, which is the intersection of sim prime submodules of M, and then the Jacobson radical, which is the intersection of all maximals. Then we have the prime radical, which is the intersection of all prime submodules of M. So comparing our local nilradical with these known radicals, we find that it is very small. It is the smallest radical that is contained in all these radicals. Next, we look at the radical ideal, which is denoted by this. That is the radical ideal of this. Just the collection of elements of the ring for which RK belongs to this, or for which these powers are inherited by M. So looking at that, we find that applying the radical ideal onto M, we find that it is actually equal to the sum of A gamma AM over all these elements that belong to the radical ideal of 0M. And in case this 0M is actually its radical ideal, if it is the radical ideal. In other words, what I mean is that if we have this equal to what is under, then taking the product of it with M, we find that this is equal to 0, and hence we find that A gamma AM is equal to 0, meaning that our module will be reduced with respect to these elements from the radical ideal. I give some references. The first reference gives properties of free radicals and radicals. The second, by Brodmann and Sharp, talks about the I torsion functor with the local cohomology. And what I have presented is actually in this paper, the local nilradical for modules over commutative rings. And Lee and Zhu are the initiators of reduced modules. They generalized the reduced rings to reduced modules. Thanks so much for your attention.